Hello everybody, welcome back today. Today we're going to be doing LeetCode number 37, Sudoku Solver. So essentially we're given a 2D array or vector essentially of characters where each character represents either an empty space, which is represented by this dot, or like the number itself, which is the Sudoku board number, right? And essentially we want to give a solution. So we want to find one specific solution of a given Sudoku board. And I'll explain how Sudoku works if you haven't seen that before in my iPad explanation. However, that is essentially the question that we're given, and essentially the output is again another 2D vector or array, and it's essentially the Sudoku puzzle solved. So let's get into the iPad and let's figure this out. I just want to let you guys know before we get on to the iPad explanation to remember to like this video, subscribe to the channel, and let me know in the comment section down below any video ideas that you guys have or anything else you guys want to see. But anyways, let's get into the iPad explanation. All right, so let's get into the iPad explanation here. So essentially, we're given a Sudoku puzzle. And if you don't know what that is, basically Sudoku is a puzzle where you're given a 9x9 board. And every element or every value in this board is going to be a number from 1 to 9. So the numbers that can be filled in are 1 through 9. And how the rules work, and I'm zooming in here, is essentially every row must have the numbers between 1 through 9 at least appear once, and at most once, in fact. So every number basically must appear. Same thing, every column must also have a number from 1 to 9, and it can't repeat numbers. So like, for example, I can't go into this place right here and make this a 9 because 9 appears twice in this column now, right? So that can't happen. And also, these yellow lines that we have here are important. They highlight a 3x3 square in that 9x9 square, right, inside of it. And so every 3x3 also must have a number from 1 to 9, and it cannot repeat. So for example, I could not also put a 9 here because this 9 already appears in a 3x3, right? So that's kind of the rules of it. And you might be thinking, hey, like this kind of seems like hard to solve. So I have the output here, and this is the output, and we can just confirm our, the rules here. So this row you see has all the numbers 5 to 2, right? And it has all the numbers 1 through 9, and does not appear more than once. Same thing here, right? This column also, you can see numbers 1 through 9 appear, but they don't repeat. And you can also see in this 3x3 right here, right? You can see also numbers 1 through 9 all appear once, but they don't repeat, right? So that's the idea here. That's kind of what this question wants. Well, you might be thinking, like, how do we actually do this? Well, people, solve these questions a lot for fun, and these used to appear on like the small magazines and stuff before. But essentially, like how you would do this as like, just for fun and solving, you try out all possible ways. Like you'd be like, hey, can I do 2 here? Can I do 1 here? Well, yeah, I can't do 1 because it appears in the same column as well as the 3x3. So maybe that doesn't work. Maybe I can put a 4 here, right? Something like that. We just keep trying possible solutions. Sometimes, you do a lot of numbers and be like, oh, this doesn't work. So you'd erase it, come back, and then try again, right? So it's kind of like that. Well, maybe we can simulate that kind of in the same manner. So how we do that is recursion, right? That's the intuition. We're building up to the intuition of how to actually do this. Well, if you want to try it all possible ways, we have to do recursion here. So I'm just going to write that here. We're going to have to do recursion. So that's the first thing. We identified like, what we need to solve this question, recursion. So now we know that it's recursion. We know that we're going to try it all possible ways. Well, what does that mean? Well, we're going to go to empty squares like this, right? We're going to go to empty squares like that. We're going to go to those empty squares and we're going to be like, hey, can I put a number there? And we're just going to put the available number that makes it possible. Like, obviously, we're not going to go here and be like, hey, let's put a 3 because we know it appears in the same row already. So there's no point in doing that, right? But we're going to check all available numbers, right? So there's going to be some kind of function that does this for us. It's going to check for like possibility, right, of a number. We're going to put the number there and then recurse. We're going to go to the next one, keep filling it up. We're going to keep filling it up until either we filled up the entire board or we get to a point where we can't fill up a number because it doesn't make the board possible, right? It doesn't make a valid board. In that case, we're going to return false, right? Returning false basically tells us, hey, this combination or this, you can think of that like recursion tree side is not valid. So we're going to keep trying another number afterwards, right? So we're going to keep trying numbers. If we can't place a board somewhere, well, then this is not a solvable Sudoku's board. But that's not going to be the case here, right? I don't think LeetCode's giving those kind of examples. So let's talk through this again, right? Again, like I said, we're going to iterate through the board. So it's going to be 2D array, right, or 2D vector. And so essentially, it's going to go for all the rows, and we'll determine the rows, right? It's just going to be the size of the m and n values, which we'll find out. And then we're going to go through all the columns, right? And by the way, this is kind of like pseudocode here, so it's not like the actual code, but this is going to talk through the idea here. So yeah, again, we're going to go through the rows and columns, and then we're going to check, hey, is the board at ij empty, right? That's the only time we're going to place any numbers, right? Because if it's not empty, we can't alter the board, to make it easier for us. Now, LeetCode, they have the empty denoted by a dot. I don't have this in my input here because it would honestly make it look more messy, but just keep that in mind, right? That it's a dot there. So this signifies an empty space, right? Empty space here. Now, we have an empty space. Now what we're going to do is like, okay, we can put any of the 9 numbers here, right? 1 through 9. So let's do another for loop, right? K starts from 1 to 9, right? Inclusive. And we're like, hey, we can put any of this. But before that, we have to check, is it actually possible to put there? So there's going to be some kind of function for this. We're going to check, hey, is it possible to put this current K value or this K number value, right, into the board? So at this current ij, which is the row column, into the board and that K value. If it's possible, right, if this is a true thing, right, that means we can actually put this, and I'm erasing these curly braces because we might need more space here. But if it is true, right, I can put these values here. What we're going to do is, okay, let's change our board to reflect that, right? We're going to change these values to K, right? And then also, we're just going to call it a recursive function. So we're going to say, hey, here's the new board, keep recursing, right? Like, keep doing a recursive function to go on to the next empty spot and keep doing it, right? Like that. And since we're actually changing the board, we won't go back to the same spot that we currently changed, right? Because it will be empty, or it won't be empty, right? So recursively call and then board. And remember when you said we're going to return true and false? That's why I have this in an if statement. What this tells us is, hey, if this returns a true, then this was a proper board, right? This was a valid board, so we actually solved the problem, right? So we return true. Else, right, what we're going to do is, okay, we altered the board here, right? And so this is backtracking. So since we altered the board, well, now we know that this number did not lead to a valid case, right? Because we didn't get a true, we got a false back from this recursive call. So we want to change this board back to an empty, right? Once we change it back to an empty, we're saying, hey, this number track did not lead us to any, valid Sudoku board. So we're just going to make that like that. And after this for loop, what does that mean? If we go through this entire for loop and we don't ever return true, what does that mean? Well, we could not place 1 through 9 anywhere on that row column square because it was not going to give us a valid, Sudoku board. So that means we could not place this. So this is return false. So that means this is where this one will lead to this into the future. It's going to be like, hey, if this is a false, then we could not place the number at all, right? So that's why when you do it recursively, that false is going to be very key here. So this is going to happen after this 1 through 9 for loop. And then at the end, we just, essentially we're done with the 2 for loops that we have. And then at this point, we're going to return true because we're essentially sure that we have given Sudoku board. Because essentially we've gone through all the rows and columns. We never gotten a false, so we just return true. That means we have a fully solved Sudoku board. So now let's talk about the main thing here, which is how do you do this possible method? Like, how does this kind of work, right? Because this is like the key here, right? This is what makes it kind of easier to understand. Well, I'm going to go down here and I'm actually going to copy, this essentially, like the empty one right here. So to explain this, we're going to essentially, you got to think about how the rules work, right? So I'm going to go to here and not paste image. We're going to paste this here. So how do the rules work? So we talked about that numbers cannot repeat in the same row. So remember this possible function that we wrote up, right? It was basically we're given a row, we're given a column, we're given the board, and we're given that K value, right? Which is going to be the value that we want to put in that row column. Well, we want to first check all the current rows. So essentially, what does that mean? Well, if you want to check the current row, right? Essentially, you're going to keep the row value, or the I value here is going to stay constant, and we're going to change the J value, and the J is going to be from somewhere from 0 to 9 because this is a 9 by 9, right? So it's going to be somewhere from 0 to 9, and 9 won't be included because this is how indices work, right? So if I write out the indices here, you see that we go from 0 to 8. But I'm just writing 0 to 9 because that's how you write it in the for loop. Same thing for the columns. We want to check all the current column, right? So we're going to keep our column constant and just change our rows, right? So then our I is going to go from 0 to 9. So you can see that row and column we can essentially handle with one for loop because the for loop is essentially just going to go from I to 0 to 9, and 9 is not inclusive, and then we can handle that in one for loop. Now we have to think about 3 by 3. How do we kind of figure this one out? Like because essentially we're going to be given like the ij. We're not going to know which 3 by 3 this actually belongs to. We cannot say like, this square right here that I have that I just erased, we cannot say this belongs to this 3 by 3. So how do we go about doing this? Well, this requires some little clever math here, and you got to think about it this way. So we are given a 9 by 9, we want to basically bring it to a 3 by 3, right? So the concept then becomes is, okay, maybe we can use some kind of division, some kind of modulus, that kind of stuff. So if you take the current row value and you divide it by 3, right? So let's say I'm at this square, right? And I have the row value, and I'm going to write the row indices right here. The row value for that one is actually 1. If I divide it by 3, I get actually 0, right? Because that's how integer division works. But if I multiply it by 3, that gives me 0 as well. So you see that now I'm getting the row 0. Same thing if I do with the column. That was my second column, right? However, 2 divided by 3 is 0 as well. Then 3 times 0 is 0. So that actually properly gave me the correct 3 by 3. But why do we need this times 3? Well, let's look at something like this. Let's look at this one right here. So this is I is going to be 2, or sorry, I is going to be 5, and then j is going to be 2. Well, 5 divided by 3 is going to be 1, just by integer division, and times 3. Okay, that gave me my third row. So that's actually this row right here, right? Now, same thing, j divided by 3 is, or 2, here in this case, 2 divided by 3 is 0. 3 times 0 is 0. So that's actually giving me 3 comma 0, which is correct. So this is actually helping us identify the 3 by 3's like start column, row and column, right? Start row and column, right? That's what it gives us. And essentially, these are gonna basically work for any ij values, right? So now you gotta think about it. Well, that helped me find it, but am I gonna actually go through that entire 3 by 3 in another for loop? Well, we could, and that'd be perfectly fine. That would absolutely work. But there's actually a clever way to do this. Well, if you want to essentially fit everything into one for loop, which is kind of a clever and clean way to do it. So if you're gonna have that for loop that we talked about, right, from I is 0 to 9, right? Well, we need to find a way that we can essentially go through these squares here from the 0 to 9, right? Well, one way to do that is, let's utilize like division again, and row, column, all that stuff again, right? So essentially, we're going to use this I variable. We have this 3 times the row divided by 3, right? And I'm calling this row here because I've called it I and j here, but not to confuse it with the for loop, because this is actually what the parameter inputs are here, okay? But yeah, row, and then 3 times column, column divided by 3. Well, yeah, this is cool. This is gonna be constant for every one of them. Now the question is, how do we change rows? Well, we want to change rows after every 3 elements, right? In that case, we want to do I divided by 3. What does that mean? Well, every 3, I'll move down 1, right? So that's what that's saying. So in this case, let's start with here. This is 0i, this is 1i, this is 2, 1i is 2, and then when I is 3, it's going to move down here. That's going to move the row plus 1, right? So that's going to work. Then next up will be the column. Now column is going to go through 3 elements, the same 3 numbers every time. Well, if that's the case, this is going to be I mod 3. That essentially means that it forces the addition of these, like the variables, like you can call this kind of an offset. It forces the offset to be between 3 numbers only, and that's going to be the case here. It's going to be between 0, 1, and 2. And that's going to work because then this is going to say, hey, first thing is I is 0, so plus 0, right? 0 mod 3 is 0. I is 1, mod 3 is mod 3 is again 1, 2, mod 3 is again 2, or right? And then when it becomes 3, then it's going to say 3 mod 3, which is 0, so it's going to come back here again, right? So you can kind of see how the column works out. And I'd suggest like kind of like follow the code, or like some kind of draw it out kind of thing, and it'll make a little bit more sense. One more thing I would like to mention before we get on to the coding solution here is that the time complexity of this solution, right? So since this is a recursion, we know it's going to be exponential. We're not doing any kind of dynamic programming, so we're not actually going to reduce the time complexity. And actually, I don't know if you really could do dynamic programming here. Yeah, there are not really cases where you could see like overlapping subproblems. So the time complexity here is actually going to be O of n, or O of 9, right? 9 to the power something. Why is it 9? Because we're actually, if you draw the recursion tree out, and I haven't drawn it out here because it would get extensively very long, but essentially, like, we have 9 possible numbers that you can put in every location. So we're going to check all those cases, right? We're recursing all those cases times. So it's 9 possible, subtree paths. So 9 to the power n squared. And reason n squared essentially being like 81 in this case, like because it's always 9, but it's n squared because we're always iterating through this 2D vector. That's going to take us n squared. So every recursive call, we're doing that. So it's actually 9 to the n squared. And then space complexity is just the recursive stack space, which is again going to be n squared because of the 2D vector space. But it's not actually, there's not actually any other external space besides that. So sometimes you could get away with just saying there's no actual external space complexity here, right? It's just the default space complexity. But yeah, now let's get on to the code. All right, so let's get into the code here. So remember, I'm doing this in C++, but you can do this in Java or any other language. The concepts do apply and transfer over, right? So first things first, remember, we essentially want to write a helper function because we're returning a Boolean, right? And then that helper function, I'm just going to call it recurse, just like how I did in my iPad explanation. So it's, it's the same for you guys to understand. It's just going to take the board. So the input for this is just the board. And I'm passing it by reference because we're actually going to change the board values. So the idea was we're essentially going to go through the row and columns, right? And in fact, let me name this row. And thing is, like, we could hard code this. We could just say 9, but just to keep it clean and like standards of coding, we're just going to say board size for the rows. And then for the columns, we're going to do int column 0, and then column's going to be less than board. And essentially, we can just take the first row size. That's just going to be the same always. So column. So now this is going through the column. And now we're going to check, hey, is any location, or at this row column location, is it empty? And as you can see, that this is the dot thing that I was talking about, right? In the input, they give you this dot, and that represents an empty location. And those are the locations we can change, right? We can't just change any number location because then that would make it easy, and that's also cheating the game, right? But yeah, if this location is empty, then we want to check what number can we put there, right? So any number between 1 and 9. Now let's keep in mind here. So this is a character type board, right? So we're gonna have to deal with characters. Well, the cool thing about characters is that we can kind of, use characters to the advantage. So basically, like, I'm going to initialize this character k here to this 1, and I'm just going to use the normal like arithmetic operators because essentially the character is a number, right? And 1 through 9, they're always in sequential order in like the character number ASCII values. So essentially when I'm doing plus plus, I'm actually going to the correct ASCII value for number 2, number 3, all the way to 9, right? So this is like a neat way to do it. Now we're going through all the numbers. We're going to have this helper function that we talked about, which is possible, right? We're going to call it possible. We're going to pass it the row, column, the board, and then the k value, right? And we're going to get into this, right? But before that, let's finish out this method here. So if it is possible, then remember, we want to change the current row column value to k, right? That board value is going to change. Now we're just going to recurse, right? Again, we're just going to call this recursive function. And since essentially we changed the board value, we're not going to ever come back to the same row column. It won't be empty, right? It will actually have a number this time. So recurse, and essentially we're just passing the board. And since we're doing a Boolean, we want to check in our recursion tree, are we ever getting a true? If we're getting a true, that means we reached a point where this is actually a valid Sudoku board, and so we can just return true here, right? Else, we're not getting true. That means we're on the wrong tree, wrong path of the recursion tree. That means we should change the row column, that same value, back to empty because, hey, this number does not work here, right? We want to try a new number. So that's why we change it to empty, and this is basically part of our backtracking, right? So that's that. And then after this for loop, if we're ever outside of this for loop, like at this point, and this line 22, that means, hey, we could not place any character from 1 through 9. What does that mean? Well, none of these numbers are possible, so this cannot be the proper path for the Sudoku board, right? So we just return a false here. It means like, hey, none of the numbers work, so how can this Sudoku board be valid? So we return false. And after we're done with all the for loops, we return a true because at this point, what does that mean? We've gone through all the rows, we've gone through all the columns, and we were properly able to place every number, as well as, we have no empty spaces. So that means this is a valid Sudoku board, so we just return true. And that, as I said, this true will reflect back here. As we backtrack, we're just going to keep getting true, 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 all the way to the top, and then we're going to be done, right? Now, let's go into that, the possible thing, right? So again, Boolean, possible, then int row, int column, same board here, but we're not going to pass this here by reference because we don't need to. However, I think keeping it by reference will probably make it, faster. It won't actually create a copy or anything. So I'm just gonna do that, but you don't need to. We're not changing any of the values here. So anyways, this is our function definition. And then basically we want to check the rows, check the columns, and check the 3x3s. Well, the row column, not too bad, right? Remember, this is basically from 0 to 9, since it's a 9x9. And so for row column, for checking the rows, we keep the row constant and then move the columns over. So we check board at row at I. And since we have 0 to 8 like index columns, right? So we check if any of these are equal to k. What does that mean? That means that this number already appears in this current row, so we return a false, right? Same thing for the column. Do any of these any of the column values, is there a k value already there, right? Then we return a false as well, because hey, that means this number already exists in this column. This cannot work. Now we come to the cool part, which is the row column for the 3x3s, right? Well, we talked about this. If, right, board, and for the row, remember we talked about the 3 times row divided by 3. So this is going to be a constant always because we're not changing the row columns here. But this essentially brings us to the starting row of the 3x3 that we're at, and to actually change onto the next row, since we're only going to go 3 rows, right? Because it's a 3x3, we do I divided by 3. So we use the fact that every 3 elements, we got to go to the next row, right? So that's what this I divided by 3 is doing. Same thing for the column. We know that the default for getting back to the start of the 3x3 column is going to be 3 times column divided by 3, right? Then we want to basically move 1 every time, but after we hit the number, like the third element, we want to reset it back to 0. So that's a modulus, right? So I mod 3 is always going to define, like, keep the value for the I mod 3 between 0, 1, and 2, which will essentially allow us to go 3 elements, and then after the third one, it's going to go back to 0, right? So that essentially lets us check all the elements in the 3x3, and it seems really like, obscure. And yeah, you could do another for loop outside of this, go to the starting locations of this. This is the key right here. You need to always know that the starting location of the 3x3 must be at the 3 times row divided by 3 position, and then the 3 times column divided by 3. And we're using the fact that integer division essentially is a floor function, right? So that's the key part here. And yeah, you could do an outside for loop and check it. That'd be fine. This is just a clean, elegant solution, right? So essentially, we're going to go through the 3x3 and check, hey, anytime it's equal to k, that means we know this number already exists in this 3x3, so this cannot be the case. Now, at the end, we're done with all the cases. We've checked all the numbers, and we're like, hey, okay, this is good. So we return a true. So remember, this is the actual function. So all we need to do is we just need to call recurse here on the board. And since they're not asking us to return anything, you just recurse on the board. And since it's passed by reference, it's going to change the board value. So let's just run this, make sure we don't have any compilation errors or anything like that. And you see, we get it accepted. Let's submit and make sure we pass all LeetCode test cases. There you go. See, we solved the LeetCode hard. It wasn't it was a hard question in terms of if you don't know Sudoku and stuff, it might seem a little more obscure, but it wasn't really a hard question, right? It used the regular intuition behind recursion where you try all things. The hard thing is coming with the idea of the possible thing, right? You might be confused. You might be like, this is going to be a very hard function to write, but in reality, it's not, right? You're just going to go through the row column, and the 3x3, you can come up with this neat solution, or you could just essentially figure out that this idea is the key here and just iterate through the 3x3 like that, right? So make sure to like this video. And so I'm hoping you're happy, you solved, maybe this might be one of your first hard questions, and it's one of my first hard questions on this channel. But yeah, make sure to like this video, subscribe to the channel, and make sure to comment down below, right? Let me know any kind of videos you want to see, but I hope to see you on the next one.